So there are a lot of scope. So this in this semester we will try to learn, we will try to know the fundamentals of this, and then if uh, any one of you can continue uh, on some field related to automata, then it will be helpful for you. Also, who all will be joining the industry and will be working in professional environment in different industries, there also you will find lots of applications of automata that you will understand as this course will go on. So the first thing that we will start with is the concept of alphabet, language, and grammar. So automata theory is the study of abstract computing devices. Now, what we mean by an abstract computing devices? Now, device we all know. A device is a physical object which using which we uh, which is meant to do some specific tasks, right? This is somehow we can define a device. A computing device means there is some kind of computation which is associated with the device, with the tasks that the device is capable of doing. An abstract computing device means that the device physically may not exist or it does not exist, but we are trying to model the behavior of the device. Just for an example, say those of you uh, who are familiar with the say football, soccer, right? So before the game starts, the coach he actually draws the formation on the board and explains that how the movements will be, right? So left out will run through this, the ball will be here, there will be a long pass. So this kind of strategies. So there is, it's actually not happening, you are not playing, but you are trying to create an abstraction of exactly what is happening on the field. So that is a very similar thing to an abstract computing device. We are not actually working with the device, but we are trying to model the computation that we can achieve with the device. So automata theory is a study of this kind of abstraction of devices, and the devices, they are termed as automaton. So automaton is a device in an abstract sense, and automata is the study of these kind of devices, right? Just a quickly a brief history of how these things come into picture. So this was started by one genius called Alan Turing. I know, I'm sure that you all have heard of this name, Alan Turing. He is famous for various reasons, but his most valuable contribution in the field of mathematics is this automata theory. He was actually, what he was researching, what he was trying to find out is that whether there is a whether there is a theoretical limit or theoretical limitation of a machine. So actually he was working on a very famous, very old problem, that logical problem, that whether you can create a concept, a machine which can answer all type of logical questions. The answer should be either yes or no, but whether there is any machine which can perform this task. So this is in the very uh, simplest terms. So this kind of a problem that he was working on, and for that, to model that, he created a machine called Turing machine, which is abstraction of a machine, but it is capable of doing everything that a computer can do nowadays. So that is the abstraction of a computer, this Turing machine. And his goal was trying to find out the boundary between what a normal machine can do and it cannot do. So Why Turing machine is important for us? Turing machine is important for us to understand what we can expect from a software. So it defines the boundary that this a software can do and this a software cannot do. Theoretically, it is not achievable. So that is what a Turing machine is, that we will study. How does it look like? How does it work? This Turing machine in the course of this in this course itself. But after Turing invented the concept of Turing machine, then many researchers they started working on simpler machines, which is not as complicated as Turing machine, whose capability is limited. And this smaller, simpler devices, they are designed to solve a set of specific problems. So it's not a general machine which can solve everything, but it's a machine which has got limited capabilities and which has got application in a very specific domain. So these kind of simpler machines they started working on, and this is called a finite automata. So these different types of machines, how they, how they behave, so that's what we will try to. And machine means a computational machine, a computer, right? So that is a brief introduction of what automata is. Now let us see an example of a finite automaton. So all of you can see my screen, right? This is a what you call state machine. There are various names with which we can call this kind of a machine. This is a machine. This is called a automaton. This is called an abstract device. This is called a state machine. And you have seen these kind of state machines in various works that you are doing regularly. For example, you are going to a vending machine, or for example, you are going to a ATM machine, right? Or for example, you are using your telephone. Say for example, you are using your telephone and you are calling one of your friend. So what happens? There is a protocol. There is a definite protocol. That means an exchange of messages before the connection is established between your phone and the other phone. First, there is a state where the phone is ready to make a call. Then you type a number or you select a name and then you press call. Then the phone goes into a calling state. So when the phone is in the calling state, it is waiting for some response from the server, from the backend. So say for example, there is a response which comes that this number does not exist. So that is a possibility that this machine it shows you this number does not exist and comes back to the start state ready for the next call. Or it may happen that there is a message which comes and it shows you that call forwarding is active, so waiting for the call being forwarded. So that is another state. So like this, the machine is, there is a transition of states from one state to another in the machine, and finally it is either accepted or rejected. Your goal is either achieved or not achieved. So that is the basic abstraction of a machine, of a state machine. Here also we can see that this is a state machine which has got three states. The states are named as S1, S2 and S3. The states are named as S1, S2 and S3. And here you can see there are two special states. The state S1, there is an arrow which is coming into this S1 from nowhere. So this indicates that this S1 is a start state. That means the initial input comes into this S1 state. So this S1 is called a start state, and this S2, you see that there are two concentric circles instead of one. So this state is called a end state or a final state. Now we can see that some zeros and ones and arrows and lines are there. So what does it mean? It's very simple. When the machine is in state 1, state S1, then if we give an input 0, let us assume for the time being that I can give input either 0 or 1. These are the two symbols only that I can give input to the machine. And whenever there is an input, the machine state transitions from one state to another, right? So that is how a machine works, as I said. So in S1, given a 0, the machine stays in S1 itself. So it's a self transition. So no state change. And in S1, if I give a 1, then the machine transitions from S1 to S2. Similarly, when in S2 I give 0, it goes to S3, and when in S2 I give 1, it remains in S2. And in S3, whether I give 0 or 1, it comes back to S2. And when, after giving an input, my state machine ends up in a state which is a final state, then we say that this string of symbols Hello, can you hear me?
Yes, sir.
So I think I got disconnected for momentarily, right? There
Yes,
is
sir.
some network issue which is there anyway. So how long I was disconnected?
Last 7 to 10 minutes.
Sorry, last
7 to 10 minutes.
7 to 10 minutes. My goodness. Okay, okay.
So you were explaining the diagrams, and
Right,
I
right, right.
think
Let me come back to the diagram. Let me come back to the diagram. So yeah, now I will periodically check my network connection every few minutes. So what I was saying is that this S1, S2, and S3 are called states. 0 and 1 they are called inputs. S1 is the start state, and S2 is the final state. As I said, that the start state must be unique, so there can be only one start state for a machine, but there can be more than one final state. So the final state is actually a set of states, right? This machine it recognizes only 0 and 1. Other symbols are not recognized, and any string, there is no restriction on the length. Any string containing zeros and ones can be fed to this machine as input. So now what happens when I give a 001? My string is 001. This is the
sir,
input.
sir, please share your screen.
Oh my goodness. Sorry. Can I see it?
Yes, sir.
Right. Thank you. Hmm. So now this is the machine and I'm giving it 001. So what happens when I'm giving a 0? It remains in S1. When I'm giving another 0, it remains in S1, and then I'm giving a 1. Then on seeing a 1, the machine transitions from S1 to S2. So after 001, the state machine is in S2, which is one of the final states. So this 001 is accepted. Right? Understood? This is how a normal computing machine works. Given an input, it transitions from one state to another, and after all the inputs are exhausted, then if the machine is in one of the final states, there can be several final states. If it is in one of the final states, then that particular sequence of inputs is accepted, otherwise
Sir,
it is
in
rejected.
this diagram, which state is final state?
In this diagram, S2 is the final state. You can see that there are two symbols. One is a arrow which is coming from nowhere into S1. This implies that S1 is the start state and the initial input is given to S1. And this concentric circle, they signify that this is a final state. So in this machine, S2 is a final state and S1 is the start state. And this is the transition that on 0 and 1, every state, how does they behave? At S1, 0 means self transition, 1 means S1 to S2. At S2, 0 means to S3 and 1 means self transition. And at S3, 0 and 1 means both transitions to S2. So now 001, as we can see, is accepted, whereas 010 is rejected because I give a 0, it is in S1, then I give a 1, it is in S2, and I give a 0, it is in S3. So After 0, 1, 0, the state machine is in S3, which is not a final state. So this is not accepted or this is rejected, right? So let us stay with this example for some more time. So let us see some longer inputs. 0, 0, 1, 1, 0, 1, 0. When I give this, we generally do this kind of computation. So at every state, I accept the input and I do a state transition. So S1 0, it goes to S1. Again at S1 0, S1. Again at S1 1, it goes to S2. From S2 1, it remains in S2. S2 0, S3. Then S3 1, S2, and S2 0, S3. So 0, 0, 1, 1, 0, 1, 0. This is not accepted, right? 0, 0, 1, 1, 0, 1, 0. But 0, 0, 1, 1, 0, 1, 1, this is accepted. 0, 0, 1, 1, 0, 1, 1. Similarly, 1, 0, 1, 0, 1, 0, we see 1, then 0, then 1, then 0, then 1, then 0. So it is in S3, not accepted. So now can you tell me what about all zeros? So if I give a string of zeros, n number of zeros to this machine, what will happen? Whether it will be accepted or not? Can anybody
Not
tell me?
accepted.
It is accepted,
No,
No, sir,
sir.
not accepted.
not accepted. And what about all ones?
Yes, sir.
Yes, sir, it is accepted.
It is accepted. Right. Now, what is the general string that is accepted by this machine? Can you tell me? Can you describe the character of the string which is accepted by this machine? Odd numbers. So if I give 0, 1, 0, 0, is it an odd number? I give 0, 1, 0, 0, it is 4. Is it an odd number? No. Is it accepted? 1, 0, 0. Can you tell me whether 1, 0, 0 is accepted or not?
Accepted.
Accepted. So it is not an odd number only. This is the characteristic of the general string. All any string with zeros and ones with at least one 1. So you need to provide at least one number of 1. Otherwise it will remain in S1. If you keep on giving zeros, then it will never go to S2. So you need to provide at least one number of 1, and the string should be ending with 1 or ending with even number of zeros. This ending with will be here. So either it ends with 1 or it ends with a even number of zeros. If it ends with 1, then it is in S2, because the first one comes here, the second one, third one, fourth one all remains here, and after a 0, if I give a 1, it again comes back here. So at any point of time, if I provide a 1, it lands in S2. So ending with 1, that string is accepted, or the string ending with even number of zeros. Whenever I give a even number of zeros, then 1, 0, 2, 0, it comes back to S2. So that is the general characteristic of the string which is accepted by this machine, right? So now Let us see some definitions to end this class. Alphabets is a finite non-empty set of symbols. So that means for the machine that we have been working so far, the alphabet is 0, 1. It's a set containing 0, 1, two elements. Conventionally, we use this capital sigma as a notation for an alphabet. Then string. A string is a finite sequence of symbols chosen from some alphabet. This you all can understand. A finite sequence of symbols chosen from some alphabet. Then empty string is the string with zero symbols. It's like empty set. Empty set is a set with cardinality 0. Similarly, empty string is a string with 0 symbols or length 0. That is the length. Length of a string is the number of positions or symbols in the string. It is not the number of symbols. So if I say number of symbols, then what will happen is, say I give you a string 0 1 1 0 1 1 0 0 0, and if somebody asks you, well, how many symbols are there, you can say 2, 0 and 1. So there is an ambiguity. So we say that this is the number of positions or symbols in the string, and the length is denoted by mod w. If the string is w, then the length of the string is mod w. So mod epsilon is 0. Epsilon is the empty string. Then power of an alphabet. If sigma is the alphabet, then sigma to the power k is the set of strings of length k taken from sigma. What does it mean? This means that sigma to the power 0 is epsilon, sigma to the power 1 means all strings of length 1, that is 0 and 1 only. If you say sigma cube, that means all strings of length 3 taken from the alphabet. So 0 0 0 0 0 1 0 1 0, all possible strings of length 3 containing zeros and ones. So the number of entries is to cube because your number of symbols is 2. If your number of symbols is n, then the then the cardinality of sigma cube is n cube, like your power set. So set of all strings over an alphabet is denoted by sigma star. It's like regular expressions. In fact, regular expression is a very important part in automata. We will study it. Regular expressions. So sigma star and sigma plus. Sigma star is sigma to the power 0 union sigma to the power 1 union sigma to the power 2 and so on. And sigma plus is sigma star minus epsilon. And finally, we have concatenation of strings. That means if x is a string 0 1 0 and y is a string 1 1 0 1 0, then xy is equal to 0 1 0 1 1 0 1 0. It's just simple concatenation, nothing else. In automata, xy means x then y, right? So please note that epsilon w is equal to w epsilon equal to w. So concatenation with epsilon, either pre-concatenation or post, does not change the string. So that's it for today. We will start with more concepts, and initially I will go a bit slower and then I will accelerate. The syllabus is large. We will try to cover as much as possible. I'm hopeful that we will be able to cover the whole syllabus in this semester, and I need your cooperation. So please do not miss the classes, because I will share these notes. Definitely, I will share these notes. But to understand the subject, I think it will be better if you attend the classes. Then we will have fun learning this subject.